Okay, hello everyone. As I talk in the intro video, I'm gonna talk about non-collapsed ancient mean curvature flow. Okay, so mean curvature flow is evolution of hypersurfaces, say in Euclidean space, and usually we just consider. In this talk we only consider embedded hypersurfaces, and yeah, this is satisfying the heat equation xt equal Laplace of x, where x is a position vector and the Laplace is a Laplace spectrum operator. And here I just say delta G, but in my follow I just write as delta for simplicity. So anyhow, here this is just a heat equation, but the reason we call this as mean curvature flow is the following. Now Laplace of x is the mean curvature vector, right? So if I have a round sphere, then everywhere I have a same magnitude mean curvature. They're all pointing the center of the round sphere. So it just shrink and converge the point. And you can see that the curvature will increase as radius decrease. So somehow it's getting accelerated. So this round shrinking mean curvature flow must develop a singularity in finite time. Singularity. And some other typical interesting model is this dumbbell-like surface. Okay, in this dumbbell shape, here it looks like a saddle. So you have the principal curvature around the neck has a different sign, but the curvature along this narrow neck has greater curvature than the other principal curvature along this flat side, rather flat side. So still, this neck moving towards the inside. And actually you can see that here, its mean curvature must be greater than the mean curvature in this some other site here. So as time goes by, sure, this shrink, but the neck shrink faster than the other part. So we develop a singularity. Okay, so in this talk, we're interested in singularity analysis of the mean curvature flow. So to be specific, we want to see what is the shape of a singularity. But the singularity is just a point. So to see the shape, we have to blow up the flow. So no, this is just a point, but if I blow up these ones to have some certain unit volume or area, then it must be just some certain fixed round sphere in this case. Around this singularity, if I blow up around the neck, then you can see that. And say we call this is neck. The neck singularity, the neck singularity converts to a round shrinking cylinder. Yeah. After blow up by taking some blow-ups. Okay, so let's talk about a bit more detailed story. So first of all, we want to see if the flow actually develops singularity. So here we can apply the comparison principle. Suppose I have a random, just a closed initial data. What? Then always, because this is closed, I mean compact. So always there is some large enough ball. And yeah, enclose the given initial data, say M1 naught. And let me say the round ball outside is M2 naught. And we consider flow from these two initial data. And as time goes by, I don't know what's going on of the original one. However, we actually just checked that this round sphere shrink to a point in finite time. And this mean curvature flow is a parabolic equation. So these two solutions cannot touch because they were initially does not intersect. Yeah, initially they didn't intersect. So by the comparison principle, I mean the maximum principle, we can somehow show that okay, they never touch, they never intersect. So, but initially the given one, M1, was enclosed by the ball, but the ball will compose a point, then no. The inside one should develop a singularity before the outside sphere develops singularity. So yeah, closed flow always develops singularity. And okay, let me just talk about one more application of the maximum principle. So if the initial hypersurface is mean convex, I mean H is positive, then mean curvature flow remains mean convex for all positive time. The proof is almost trivial. I mean, if we derive the evolution equation of H on the flow, H satisfies this parabolic equation, and A is squared. So we can consider it's minimum. Then the maximum principle, or say minimum principle, shows that H is greater than the infimum of H at initial data, which is positive. Yeah. So if initial surface is mean convex and remains mean convex, so we frequently call this mean curvature flow with the positive mean curvature as a mean convex flow for simplicity. And actually, you can show up with more stronger statement by using maximum principle that if the initial data is convex. So yeah, say if the initial data is closed and convex, then the minimum principal curvature kappa satisfy this property. I mean the ratio of this kappa minimum and H preserve its lower bound. And initially it was positive, so yeah. The ratio has uniform lower bound. The proof is, yeah, the proof is pretty simple. Again, consider the evolution equation, then we can somehow show this. So the kappa mean is a super solution to the evolution equation of H. So apply the maximum principle for the ratio, so you can show the visual statement. And there is a nice application of this pinching instrument. This is so-called the pinching instrument. And in that case, MT converge to a point. Okay, so this is convex. So when it disappears, it must disappear in a point or a line segment or some say plane segment, whatever, because it must be, the limit must be convex. But you can imagine that if the limit is not a point, then it's converted to say some line segment whatsoever, was part of plane. So somewhere the curvature should degenerate to 0. However, pinching estimate above says that kappa mean is bounded by some constant times h, but we already checked that h has a uniform lower bound. So yeah, kappa mean has a uniform lower bound too. So it is impossible to get some 0 principal curvature to limit. So the limit must be a point. Actually, one can walk very hard. So I don't want to tell details because this is pretty difficult. So we can shows that in the convex closed flow converge to round sphere after rescaling. Oops. So, I mean, even though the initial data looks like an ellipsoid, sure, it's still shrink, but it's getting more round, and converge to point. I mean, if you lower the flow by rescaling, the limit is the exact round sphere. So in this, so we say, in this case, we say, okay, mean curvature flow converts to round point for simplicity. Then yeah, this is a nice result. If initial data is convex and closed, then it must convert to round point as like a shrinking sphere. So pretty rigid. Okay, but still, yeah, we can obtain sort of a pinching estimate from in convex case. So we can see X shows this inequality by using again, and this is not maximum principle, this is Stumpach iteration, but anyhow, to me, Stumpach iteration is kind of a difficult version of the maximum principle. But anyhow, yeah, so yeah, we can obtain this, and this is somehow very excellent. It's very amazing result because, you know, this somehow says that at the blow limit, the rescaled flow convert to convex flow, even though the flow was just a mean convex. So mean convex guys develop a convex singularity. Why? So if you divide by h, because h is positive, so we can divide by h. So kappa mean over h is greater than here some eta minus constant over h. And eta is an arbitrary small positive number, and c depends on eta and the initial data. And you can imagine that at the singularity, h must diverge to infinity, right? Because h is comparable to a squared in convex income. No, not really. In convex case, they're comparable. Sorry. But yeah, yeah, somehow, I mean, A is another regularity theory, but H is bounded better. Yeah. I mean, we can consider some singularity where H diverges to infinity, then yeah, C over H converge to 0. So this disappear to 0, and this disappear as 0. And then, you know, we can choose at arbitrary small. So at the limit, we can expect that kappa mean over H is non-negative. Yeah, heuristically. So we can expect the convex limit. So actually, yeah, we need to prove a little bit further, but we can show, we can say this phenomenon of mathematical as follows. So given a main curvature flow MT, and say x naught t naught is singularity, and we consider a sequence of triple that xi is converted to the singular space, and the space points of the singularity x naught, and t converted to t naught. And the scaling factor lambda diverges to infinity. Then we define these dilated mean curvature flows. So this flow is just obtained by dilation of the mean curvature around the singularity. So space-time diverges to infinity after shifting the singularity to space-time origin. Then, in case the sequence of rescaled flow has a subsequential limit, then we say that okay, say the limit, say the m bar is a limit, then the m bar t is the limit flow. And actually, we expand the space-time from the origin. So you can check that this limit flow must be ancient. I mean, it exists from the negative infinity. So by definition, we know that this n is defined for negative infinity to 0 by definition. And okay. And one more thing. So if we fix xi and ti as x naught t naught, then the limit flow is called as a tangent flow. This is kind of the same concept to tangent cone of the minimal surface at the isolated singularity. And so by using blow-offs, we can find the limit flow, which must be ancient. And then something special limit flow is some specific limit flow is limit flow. Okay, it is kind of a special case. And by using physics semester, you can somehow show that if the initial, mean convex flow. To use a physics semester result. You need the mean convexity, right? So, okay. So if T is a closed mean convex flow, and then the limit flow at the first time singularity x naught t naught is convex. Okay. Now let me compare a bit about tangent flow and limit flow. I mean, in here I say it's a limit flow, a tangent flow. Why? Because the limit flow is not unique. Yeah, that's the reason we distinguish somehow the limit flow and tangent flow. So again. So I'm gonna construct an example of the mean convex flow. We just say rotational symmetry. And so, here it looks like say tip, and this tip has a greater mean curvature than the other part. So these guys develop a point singularity before the entire flow develop a singularity. So this is finite time singularity. Okay, let me say this singularity is x naught t naught. And we can choose the tips, actually the tips of the flow as x0 t0. So one, whatever, in this one. Sure. x0 would be different from this xi's. Then something interesting is that in this case, tangent flow is a round shrinking cylinder. As like just dumbbell neck. But the limit flow along this tip axis is ball soliton. So this ball soliton is not shrinking flow. So cylinder and sphere is actually shrinking under the flow, but this ball soliton is translating. So I mean, this is kind of a traveling wave. So this travel with some constant speed. So everywhere it has a constant speed vector. So it does not shrink, does not expand, and just shoots out with the unit some fixed speed. Okay, sure, with a fixed direction. And something interesting is that this is rotation symmetry. So here, yeah, this has S and -1 symmetry. Actually, in this 3D case, it's S2 symmetry. No, S1 symmetry, sorry. Yeah, because this is R3, we have S1 symmetry. So, or O2 symmetry, whatever. And same in S1 symmetry, or O2 symmetry. So, you can see that because tangent flow is a limit flow. So at the same singularity, we have a multiple limit flows. Yeah, and they depend on choice of rescaling, center of rescaling size Ti. And then what is the typical ancient flows? They are self-similar solutions, self-similarly shrinking solutions, and self-similarly translating solutions. Here, cylinder is a shrinker, and ball is translator. And actually, we are considering convex case. So let me quickly give some example of a convex translators, which is a convex ancient solutions. So first of all, green reefer in R2. So green reefer curve is a kind of a one-dimensional version of the solution. So R2. These guys also just translating, but something different is that this one asymptotic to two parallel lines, while this ball soliton actually look like a paraboloid. Yeah. So this is quite important difference. I'm gonna explain it later when I talk about the non-collapse things. So in R3, we can make a green reefer cross R. I mean, consider some, this green reefers. Oops, very weird picture. Sorry, how to draw it? Like this, I don't know. This way, no, green reefer cross R. R3. This is clearly on convex. ancient flow. And we also have a wing solitons. And looking like this. It looks like a triangle. So asymptotic to actually triangle, but we have a granules here with the same width. So actually, something interesting is given a narrow angle data, we can always find the wing soliton. So this wing soliton, interestingly, also translating soliton, convex. So there are too many examples of convex translators, which is compensation solution. Actually, there's even more examples. Actually, there's infinitely many. But yeah, let me skip about that. So it seems almost impossible to classify ancient living flows. Sure, we can somehow see some structure, maybe. Yeah, there are some papers, but yeah. But let me skip because there are so many things to talk today. Okay, so yeah, let me talk about how to classify the limit ancient flow. So to do this, let me just first consider tangent flow, then infinity of the limit flow, or just ancient flow. So given a hypersurface sigma, we can define a functional, say, entropy in this way. Yeah, this is a bit very complicated, but maybe you don't need to. Yeah. Let's see. Let me skip the details. So something I just want to tell you about the entropy is that this is invariant under rescaling, some dilation, and translation and rotations. So all the rigid motion. So entropy is invariant under rigid motion and dilations. So self-similarly shrinking flows or translating solutions. I mean, all the self-similar solutions has the constant entropy under the flow. And moreover, for any mean curvature flow MT, the entropy is decreasing, monotone decreasing. And actually, in general, there's a strictly decreasing. And yeah, it must strictly decreasing unless it is a self-similarly shrinking flow. But actually, sorry, translator also have the constant. So, sorry. Okay. Let me a bit fix. So say this is let me say this one as, let me define this as theta at y r. Then sorry, I have to talk about, I have to say yeah, just a self-similar flow. Actually, I mean, okay, let me talk a bit more careful. So this entropy is kind of a stream between the stream for the rescaling and the choice of center for the Friskin monotonicity. See the paper of Friskin's paper in the 90, and then sorry, the Friskin monotonicity. The Friskin monotonicity there, the Friskin shows some certain monotonicity for some functional looking like this entropy, and then the functional, the monotone functional, say energy whatever. Strictly decreasing unless there is a self-similarly shrinking flow centered at the given space-time center. And then the entropy is just primo for the choice of rescaling system. So for the choice of center of the monotonicity. So, okay, let me erase this part. My bad. And just monotone. Okay, sorry. Yeah, then that is perfect. But anyhow, so still, but we can somehow use the self-similarity for the constant physical monotonicity for fixed center. So we can show this corollary. Say, for given ancient flow, we consider this blowdown. Right? Here, Ti diverges negative infinity. So this is just a blowdown of time slices. And then these guys should converge to some planes with plane with multiplicity or around the sphere or around the cylinder. Why? Because if this is a linear ancient flow, then by definition of blow-up, it has a uniform upper bound obtained by, with the bound is entropy of the initial data of the original flow. So this has some certain fixed bound, but this entropy decreases monotonically. So the entropy defined for the unit time convert to 0 as t goes back. So which means that somehow we can show that mt behave like self-similarly shrinking flow at t very negative. And then the only self-shrinking, the only convex self-shrinking solution is plane around the sphere or around the cylinder by the result of rescan. So the substantial limit must be planes, sphere, or cylinder. But in case that is a sphere or cylinder, because of the mean convexity, it must be multiplicity 1. Because if it has a positive mean curvature, then the flow foliates the space. But if that is if the tangent flow looks like a sphere or cylinder, then and then with the multiplicity, then it cannot foliate the space. You can imagine geometry. But plane can have multiplicity, like these cases. These guys is converted to plane with the multiplicity 2, because these parts look like 2 planes. Also, these parts look like 2 planes. So as time goes back, this guy goes in this way, and this guy goes in this way as time goes back, right? So if you fix the center, if you see what happened around the space origin, then it becomes like 2 planes, right? So this is convex, but the tangent flow at the infinity, backward infinity, is plane with multiplicity 2. So this is a sort of a headache. So we have to see what's going on for the plane with the multiplicity and just a single plane or a single round sphere and single round cylinder. Let me talk about that in the second part.